Okay, this is our last use of the gas loss simulation. All right, we're going to be looking at the relationship between pressure and temperature this time. Okay, so again, simulation link is right here. Should also be somewhere on Schoology. This, again, I forgot to change, should be U3 Lab 3, and this would be pressure and temperature, not pressure and volume. All right. Okay, again, we're sticking with the ideal setting. It's going to be kind of your leftmost option. We're going to look at the box when there's no particles in there, which should tell us there is no temperature and no pressure, since there's nothing to measure the pressure and temperature of. So again, I need particles. Launch some in there. Okay, and this time, since I want to see how pressure and temperature change with each other, I want to hold volume constant. Okay, so you might notice my handle is gone. I can't make my box bigger or smaller. Okay, so the size of my box is not going to change. If you want, you can check off the width, but you don't really need it this time. So in this case, I just want to see the relationship between the temperature and the pressure, these two right here. So I've got my bucket down here, so I can add in heat or remove heat, and that should change the temperature and it should change the pressure, but the size of the box is not going to change this time. Okay. So before we put any particles in the box, you could predict if, after we put particles in the box and we have volume held constant, we can predict if increasing the temperature will increase the pressure or decrease the pressure or make it stay the same. And then actually go and do it, add in some heat, see what happens to the temperature and see what happens to the pressure. And then we can start recording data. So we've got another data table here where we want to keep the number of particles constant. Right now I've got about 100 in there. But again, it doesn't really matter how many you have. It could be 100 or 200 or 150 as long as you've got enough room in your box. And as long as you keep this constant throughout, we're good to go. Okay, at these temperatures, we're going to see what our pressure winds up being. Okay, so for instance, switch back here. I crank my temperature up to 600 Kelvin or somewhere close to it. It's a little hard to get right on. Ooh, that's pretty close. Ooh, 98, 630, 599. Oh, okay. I want to settle on 599. Pretty close. My pressure is about 23 point. It's kind of floating around there. Maybe like 23.4 or 3 atmospheres. I'll do 23.4. 600 Kelvin. My pressure is about 23.4 atmospheres. Okay, we can do that for the other temperatures too, for 300 Kelvin and for 900 Kelvin. Most likely you'll probably already start at 300 Kelvin, so you might get a free piece of data right there. Okay, now we've been doing all this stuff with the heavy particles, but what about the smaller particles? So let's go back to the simulation. Okay, so I'm going to open up my particles box. Yeah, I got 100. And using the big double arrow, I'm going to remove all my particles. And then I'm going to change this pump to have these little red particles instead. These guys are lighter, okay, which means they're going to be moving a little bit faster. Okay, I still got volume constant, which is good. Okay, my particles are bouncing around. Nice. Okay, so just by looking at it, you can see a difference, right? Well, let's see what else we can kind of figure out. So, okay, yeah, we're switching to the red, smaller particles. Now, just to, kind of show this too, you can also just use this down here to remove or add particles without using the pump. Either way works. It doesn't really matter which one you choose. Okay, but either way, once we get some red particles in there, We've got another table on the next page that's got a similar kind of setup. Okay, again, this is something I forgot to change. This should be just one set of particles that we keep constant. So in this case, I've got 100 particles. In this case, you want to keep your number of particles the same as before. So again, it doesn't really matter if you used 150 blue particles at first, but if you use 150 in the first one, you want to use 150 in the second one. Okay, if you got 125 blue ones, use 125 red ones too. So that way we can really compare them. Okay, so that way the number of particles is not a factor that's changing our data. Okay, other than that, same idea. What does our temperature do to our pressure in the container? Okay, well, as we change these here, we can see what pressure we get as we heat up or cool down the box. So let's add it to me. Let's go to 600 Kelvin again. Oop. There we go. Pretty close. 601 Kelvin. We've got a pressure of about, well, it's about 23.4-ish atmospheres. It's kind of floating around there. Okay, so about 23.4 atmospheres. So very similar to the pressure I had for my blue particles. Okay, even though the blue ones were bigger, it's just kind of interesting. All right, you got some questions about this, about how the pressure relates to the temperature. Okay, what you notice here. Okay, compared to each temperature, the pressure of the blue or heavy gas are much higher than, about the same as, or lower than the pressures of the red gas. So you can kind of look at that. You can also look at that about how fast they go. Okay, so I mean, our pressure was pretty similar at the same temperature. Not much change there, even though the blue particles were moving way slower than the red particles. The heavy particles moved slower than the fast particles. And there's a reason for this. Temperature doesn't just depend on speed, it also depends on mass. If I'm going to get hit by something going 10 miles an hour, I'd probably rather it be a bike than a truck, for a good reason. Kinetic energy is not just about how fast something goes, it also depends on how much mass is moving. So in my simulation, just to kind of demonstrate this, I'm going to put red and blue particles in the box at the same time. Okay. So very easily we can see that our blue particles, our heavier ones, are moving much slower than our red ones, and yet everything in this box is at 601 Kelvin. Our temperature is the same for all these guys, okay? I didn't just add in a bunch of slow particles and then my temperature just suddenly dropped because they're all moving slow. Because speed is not the only factor in the kinetic energy of a sample, okay? The temperature of a sample, the kinetic energy, also depends on how big those particles are that are moving. So while a blue heavier particle is slower, it's also got more mass to carry with it. It's got more momentum, more inertia. So it's got a little bit more kind of energy behind it, okay? So everything in this box is at the same kinetic energy. This whole box is at the same temperature, okay? Because it's not just about speed, it's also about the mass of the particles, okay? The lighter particles can move faster but don't have as much mass, okay? But they end up having the same impact as the blue particles when they hit the inside of the container. You know, whatever they are lacking in mass, they make up for in speed, okay? And that all comes together as the temperature. Now, the way that we look at temperature for particles, okay, where it's the average kinetic energy, is part of something we call the kinetic molecular theory, okay, which is essentially a set of simplifications of how we deal with gases. Okay, and some of the stuff we've already seen in particle theory, and this is essentially the same kind of thing. I mean, molecular is just talking about particles. You know, theory is still there. Okay, and then kinetics all about motion. So the motion of particles theory essentially is what we're looking at. This is, not a whole lot new going on. So there are some simplifications that we take in the kinetic molecular theory to make gases easier to understand and deal with, including that gases are hard spherical particles. If you ever look at a water molecule, okay, a particle of water looks something like this. Okay, you've usually got one oxygen atom that's colored red. It's pretty big. You've got these two kind of smaller atoms here, and usually we use white to show hydrogen. Well, that's going to bump around a little bit weirder than just a simple sphere, something like that. Okay, so more complicated gas particles are going to be a little bit harder to predict how they're going to move and how they're going to attract or repel each other. So we a lot of times just simplify them to be hard spherical particles. We just kind of wrap them up in a bundle and say this is a gas particle, one big sphere, okay, rather than their actual shape. We also assume that particles move in straight lines, okay, until they have a reason not to, until they collide with something. So if this is my box here, my particle right here might bounce off here, and then go this way, and then bounce this way, and bounce that way, and keep going and going and going. So they don't all of a sudden just like swerve and, move around and stuff like that. Now, in reality, there's a lot of things that affect the motion of particles. So it can be hard to, say, well, yeah, they're always just going to go in straight lines. But in our case, this is our simplification. We're going to say that they go in straight lines until they have a reason not to. And it's a little bit hard to see that in your simulation. Okay. So inside the box here, I have both blue and red particles. I'm going to remove some of these so it's a little bit easier to see. Okay, let me get just a couple of these bigger particles. Because they're moving slower, you might be able to kind of keep your eye on one or two of them and notice how they move. Okay, they only change direction when they hit something. Okay, whether it's the wall or another particle. Okay, and their energy is always conserved. Okay, that's going to be another important part here. And that means that whether they are, running and hitting each other or the wall, they don't kind of slow down for no reason. They're giving their energy to something else. And our temperature is going to stay about the same, throughout this. Switch back to the lab. Okay. Now, since I emptied out a bunch of the gas particles, this looks pretty close. Most of the gas is empty space. And this is a simplification that works very well for us in chemistry. But in your simulation, it's a little bit hard to show because we want to see the particles running into stuff. So a lot of the stuff we do in the simulations, we load it up with 100 plus particles and they're all banging around. So it doesn't look like a whole lot of the gas is empty space. But there is a whole lot of empty space in a gas in between particles. It looks like a lot of space is taken up because the particles are moving so fast with so much energy that they keep their container sort of quote unquote filled. Okay. So our simulation shows a lot of these simplifications really well. So like, for instance, gases are hard spherical particles. Yeah, whether it's the blue particles, the red particles we're throwing in here, they're spheres. They're little round circles. So we could check that off. If you see something that doesn't seem to kind of fit into our simulation, okay, that we're not showing the simplification, we don't check it off. So for instance, most of the gas is empty space. If you've really packed in your simulation with a bunch of particles and you don't really kind of go along with that, then maybe you don't check this one off. Okay, other simplifications to watch out for. Again, particles don't attract or repel or cling to anything. In reality, gases have a little bit of attraction to each other or a little bit of repulsion as they pass by each other, even if they're moving very, very fast. There is an effect for that. But for our case, we can kind of simplify it to the extent that we kind of ignore it. Okay, no energy is wasted or lost from collisions. So in reality, as stuff bumps together, you have heat transfer and you have friction, including with the container. So if we have a hot gas in a container, it's going to start to release some of that energy out to the outside rather than just passing it from one particle to another. But in this case, we're going to assume that all the energy stays in the particle somewhere. So maybe one particle bumps into another and they transfer energy to each other, but that's all still there for the gas. Okay, so it all stays the same temperature. Finally, temperature, and that depends on To wrap up, we just have a couple conclusion questions that tie together how pressure and temperature relate to each other, whether it's in the simulation or on the real world scale.